Okay, so we will continue our study of limiting values for functions involving polynomials. And this video will concern limits for x tending to 0, but then from the right. We will illustrate what happens by a few examples. And the first example is the following. We consider the limit for x tending to 0 of the function x to the power 2.5 plus x to the power 3/2 plus x to the power 1/2 divided by 2x squared plus 2 times x to the power 1/2. Now the first thing that you do is to simplify. So cancel common terms in both numerator and denominator. And if you look at this, well, you don't care about the constants, we only care about the powers of x. Now the common terms in both numerator and denominator is x to the power 1/2. So we divide by x to the power 1/2. Everywhere, all terms, and we get, well, what is left if we divide by x to the power 1/2? We get x to the power 2 here in the first term of the numerator, plus x to the power 1 in the second, and the third becomes 1. And in the denominator we get 2 times x to the power 3/2 plus 2 times x to the power 0 is 2. And what we do now is, in fact, plug in the limiting value and see what happens. Now what happens here? We get 0 plus 0 plus 1. And in the denominator we get 2 times 0 plus 2 is 2. So we get limiting value. If we plug in the limiting value, we get 1/2, and this is in fact the limit. The second example is similar, but we now take another function. We take x to the power 3 plus 2x plus 5 divided by x to the power 4 plus 1. Now here we have no common factors of x, common powers of x that we can cancel. So we leave it like that. We plug in the limiting value, and then we get 0 plus 0 plus 5 is 5/1. And what we get is a nice, no problematic number. We get 5. This is the limit. And what we did was plugging in limiting value. Now, why do we have to cancel common terms? If you look back at the previous example, if we would have plugged in the limiting value in the non-simplified version, we would have got 0 divided by 0. So it's in fact to avoid that situation that we cancel the common terms. Now there's something special about this example as well, because if you look at it if you compare these both examples, then the highest power in the numerator is higher than the one in the denominator. In the first example, in the second it's reverse, and so we might expect some different behavior, but in fact the behavior is the same. The third example has the same structure as the second, but a little bit different. We skip this 1 in the denominator. We write x to the power 4. And if we now plug in, of course, if you look at it, we cannot simplify. So we plug in the limiting value directly, and what we get is 5/0. Now, as we saw in the previous movie, that in such a situation it means that the limit is either plus or minus infinity, and you can test or check this by plugging in a very small number, small positive number. So, for instance, 10 to the power minus 6, 1 over a million. But of course, when we look at this expression, you see that these are all positive terms in numerator and denominator, so it must be positive. So if we have the choice between plus or minus infinity, we must have plus infinity, and so we get this result. So in fact, the role we have a different situation from quotients of polynomials if we consider the limit for x2 tending to 0 compared to the case where we have the limit for x tending to infinity. And what is the procedure? If we formally now describe it, what you should do is first simplify, cancel the common powers of x, and the second is plug in limiting value, and again we have two situations. If the answer is a non-zero number divided by a non-zero number, then this is the limit. Then we have the limit that we wanted to compute. And if it's a non-zero number divided by 0, then we have limit that the limiting value is either plus or minus infinity, and we can test this as I mentioned before. So you always have to plug in a very small number, and if 10 to the minus 6 is not small enough because the constants that play a role are much smaller, then of course you take an even smaller number, but in general with the usual functions that we consider, say 1 millionth should suffice.